Welcome to the Explainer. Have you ever actually stopped to think about what powers our modern world? I mean, we usually picture moving gears, burning fossil fuels, or massive spinning turbines. But there's a hidden engine running almost everything around us, completely silently, without a single moving mechanical part. Today, we're unlocking the fascinating, invisible world of electrochemistry. So here's a weird question for you. What connects your smartphone, a rusting bridge, and your own nervous system? At first glance, they seem like totally unrelated things, right? You've got high-tech gadgets, decaying infrastructure, and pure biology. But believe it or not, there is a single unseen link driving all three of these phenomena. Okay, let's dive into this. Electrochemistry is that hidden link, and look, I know that sounds like some abstract theory you'd only ever use in a chemistry lab, but it's our daily reality. It's the rechargeable battery in the device you're using to watch this right now. It's the heavy lead-acid battery firing up your car. It's the unwanted rust on an old iron gate, the shiny chrome on a motorcycle, and even the tiny zinc air cells in hearing aids. Actually, it's literally inside you right this second, transmitting nerve impulses through your nervous system using sodium and potassium ion gradients. It's how we make household bleach, how we get the aluminum foil sitting in your kitchen, how we power EVs, and even how breathalyzers work. It is absolutely everywhere. So what exactly is it? Well, think of electrochemistry as a crucial bridge connecting two totally distinct worlds: chemical reactions and electricity. And honestly, the most mind-blowing part about this entire field is that this massive global engine is driven entirely by the movement of tiny invisible particles, electrons, just shifting from one atom or molecule to another. Now, this invisible engine basically runs in two opposite directions. On one hand, we have spontaneous reactions. This is where certain chemicals just naturally want to exchange electrons. If we keep them separated and force those electrons to travel through a wire, boom, they release energy. That's a battery. On the flip side, in complete reverse, we have non-spontaneous reactions. This is where we take electrical energy from a wall outlet and pump it into a chemical mixture to force changes that would never happen on their own. Things like splitting water into oxygen and hydrogen, or purifying metals. So it's the natural release of energy versus the forced chemical change. Section 1. Galvanic cells and the Nernst equation. Let's look a bit closer at that first direction, the natural spontaneous release of energy. A galvanic or voltaic cell is really just a system designed to take the chemical energy from a spontaneous redox reaction and convert it directly into electrical energy. When you first build one of these cells, its standard potential, the voltage, depends entirely on the nature of the electrodes you choose. But as we all know, that voltage doesn't stay constant forever. Now, what's really interesting about this slide is how some seriously intimidating math perfectly dictates a highly frustrating everyday experience. Take the Nernst equation and your TV remote. When batteries are fresh, the voltage is high, and your remote works perfectly from all the way across the room. But over months of use, the chemicals inside deplete. In the math, this means the reaction quotient, Q, increases. The Nernst equation beautifully dictates that as Q goes up, the overall cell potential, E cell, inevitably drops. And just like that, the remote dies. The math literally dictates your dead batteries. Section 2. Electrolysis and Faraday's laws. All right, let's flip the engine over and look at the other side, using direct current to force a change. Electrolysis is simply the process of taking electrical energy from an outside source, like an external direct current, and pumping it into a chemical mixture to drive a non-spontaneous chemical reaction. And this brilliantly illustrates exactly how we control this forced reaction through Faraday's first and second laws. They essentially state that the mass of a substance deposited at an electrode is directly proportional to the total electric charge passed through the electrolyte. You probably admired a shiny metallic fence or spotless new hardware at the store, right? Well, that's electroplating. A factory dips unrefined metal into a solution and applies a steady current I for a highly specific time, T. By strictly following Faraday's laws, they can precisely control the deposited mass, M, ensuring a perfectly uniformed protective layer of zinc or chrome. We are literally painting with metal using math. Section 3. Conductance of solutions and Kohlrausch's law. But how does the electricity actually travel through these chemical solutions? We aren't just moving loose electrons through a solid copper wire here. We're moving whole chunky ions through a liquid. I want you to picture this. It's a freezing winter morning. You get into your car, turn the key, and nothing. Just that incredibly slow, struggling, clicking sound of an engine completely failing to start. We have all been there, and let's be honest, it is the absolute worst way to start a day. Well, that struggling clicking sound is basically the temperature dependence equation playing out in real time. In solutions, electricity is conducted via the movement of ions. When the temperature drops, the conductivity, denoted by the Greek letter kappa, drops significantly along with it. The sulfuric acid electrolyte inside your car battery gets way too cold. And because of this temperature dependence, the ions simply cannot move fast enough in the freezing liquid to deliver the massive burst of current required to turn over that heavy engine. Your dead car battery is really just an equation reacting to the cold weather. Section 4. Electrochemical thermodynamics. Look, we simply cannot talk about physical chemistry without bringing it back to the ultimate unifier. Everything we've discussed so far comes down to thermodynamic principles, specifically the change in Gibbs free energy. Think about your smartphone again. During the day at school or work, it's discharging. That's a natural, spontaneous process. But at night, at home, you're recharging it, which is a non-spontaneous process. So the crucial point is captured right here by these equations. For your battery to actually provide power so you can scroll, text, or watch this explainer, that spontaneous process, the Gibbs free energy, delta G, absolutely must be negative. But when you get home and plug it into the wall adapter, you're supplying external electrical energy to overcome natural thermodynamics. You're forcing a non-spontaneous reverse reaction, meaning delta G becomes positive, pushing the energy back into the battery to get you ready for the very next day. Let's move to Section 5, Solid-State Battery Innovations. Let's see how this builds into the absolute cutting-edge future of energy storage. You know the biggest limitation with current battery technology, especially those massive ones used in electric vehicles? It's the liquid electrolyte inside them. It's highly flammable, and it can be incredibly dangerous if the battery is damaged. The solution? Solid-state electrolytes. These are advanced solid ionic crystalline compounds engineered to completely replace those risky liquids, offering significantly better safety and much higher energy density for modern transportation. But wait, how do you make a solid that actually lets electricity flow as if it were a liquid? Well, scientists are currently using the Born-Landé equation for lattice energy and formal charges to engineer these solid crystalline materials from the atomic level up. By perfectly calculating these atomic charges and the strength of the crystal lattice binding them together, they can create a solid matrix that allows lithium ions to flow freely, completely without the risk of the battery ever catching fire. This mathematical engineering is exactly what's making the next generation of electric vehicles a reality. And finally, Section 6, Pioneering Our Energy Future. Which brings us to the grand finale of this explainer. Why does all of this microscopic math actually matter to us? The real-world stakes here are massive, both personally and globally. For the students watching, absolute conceptual clarity on thermodynamics, distinguishing between standard and non-standard conditions, and mastering redox equations. That is exactly what separates the top rankers on brutal entrance exams like IIT-JEE, NEET, and BITSAT from everyone else. But guys, it goes so much further beyond just passing exams. Humanity is rapidly trying to transition away from fossil fuels, and the world is desperate for brilliant minds in material science and green technology. The exact principles and equations we looked at today, those are the literal tools you need to engineer higher capacity EV batteries, to develop hydrogen fuel cells for public infrastructure, and to design advanced methods for capturing carbon. So I want to leave you with this final, provocative thought. Are you going to simply memorize these concepts just to pass a test? Or will you take this knowledge, internalize it, and use these very equations to pioneer the next generation of global energy solutions? The future is an invisible engine, and electrochemistry holds the keys. Thanks for joining me on this explainer. I hope you found these concepts as fascinating as I do, and I'll catch you in the next one.